50 seminars. And this time it's a pleasure to welcome and thank a lot Laura Schulz for being here. And so she's head of the department of the Leibniz Supercomputing Center in Munich. Yes. But I guess that the way she arrived at this position is pretty non-standard, no? Because you are biologist from education, actually not just degree, no, also the PhD. Yeah, but then she went to the United States. You did an MBA or something like that on some formation in management, and then well, through several instances like the Lawrence Laboratory, no, you started collaboration with the HPC departments, and now she's back in Munich since 2016, no, or 17, more or less, yeah. And so she's head of this important institution, this Leibniz Supercomputing Center. So we have many things in common. I mean, this is Quantum Spain is a project that aims also to disseminate quantum computing and foster it in Spain. So we are eager to hear about your experience and your projects. So the title is we're HPC. No, I don't have it anymore here in front of me. Okay, so something like where we are, where we need to go, something like that, yeah? And not with this stronger statement that where we want to go is where we need to go. Yeah, we might want to go somewhere, but we need to go somewhere, yeah? So Laura, the floor is yours. Thank you very much for being here. So it's a pleasure.
Well, thank you. Thank you so much for having me. And it's a real honor. And yes, of course, I know quite a bit about Quantum Spain. Actually, one of the folks on my team is going to be there, I think next week, actually, for a 2-week summer school that's hosted, I believe, by Quantum Spain, or in conjunction with. So yes, I know Alba pretty well through our interactions at the European level, and I always have a very warm, soft spot for Spain. I love the country, so it's a real honor to speak with you today. So thank you for having me. So so my name is Laura Schulz. I am the head of quantum computing and technologies at LRZ. Before that, I was head of strategic development and partnerships in the supercomputing space. I was previously at the Lawrence Livermore National Lab. So I am an HPC girl through and through, but as you mentioned, I kind of have a wandering career path, starting as a domain user and then slipping into the HPC space, and now in quantum. So today, I've looked at your YouTube channel, and so real kudos to you for this series. It's really very interesting. I thought today I would give you a perspective from an HPC center. Of course, you have Barcelona and CESNA and others in Spain, really great institutions. From our perspective, I thought I would give you an idea of what quantum looks like from our end, what we're dealing with, what we're trying to do to bring quantum into the HPC world and to make it really usable for users as another very powerful tool in our compute toolbox that we have. So I thought I would title this Where We Are and Where We Need to Go, to kind of give you some ideas of what we've been facing the last 2 years and kind of how we see the perspective. And then of course it would always be really great to get your input and to maybe foster some more collaborations between us. So before I start, I want to send a warm greeting to you from my team. This is not all of them, because I can never get them in one space at one time, but this is a bit more than 2/3 of my team. And they're a fantastic group of people, from computer scientists to physicists, theoretical and experimental. We have software developers, program managers, just a really nice mix of folks with lots of varied backgrounds, representing easily over a dozen nations, and just a fantastic team of very bright people that we're bringing together to work in this very multidisciplinary hybrid space. So greetings don't come just from my team, but also from Munich Quantum Valley. So like Quantum Spain, this is an initiative at the state level for the state of Bavaria in the south in Munich. And my goodness, if you haven't been to Munich, the weather is wonderful in the summertime. So please do stop by. And if you do, shoot me an email and I'd be happy to meet with you. But the Munich Quantum Valley is this initiative that started a few years ago from the state of Bavaria. And basically they took a significant investment, several hundred millions of euros, placed it in this program, bringing together the Bavarian Academy of Sciences, under which LRZ falls, with Walter Meisner Institute that you may have heard of for extreme cold temperature science, the DLR, NASA, the Fraunhofer, the two universities of excellence in Munich, LMU, and the Technical University, and Max Planck. So basically, there's all this brain power in this area of Munich, and they put the Munich Quantum Valley together really with the express purpose to develop and operate competitive quantum computers within Bavaria. And because of the institutions that we have a couple of different technologies that we're looking to bring up and to develop. And so we have superconducting, we have ion trap, we have neutral atom. Those are the three primary technologies that are being developed and then spun out. And then our job at Leibniz Supercomputing Center, again, I said we're an HPC center, big data, AI, future computing. Our job is to take those systems and to bring them into the HPC environment, to connect them into the HPC workflow, and to really help bring a new accelerator capability coupled with the decades of experience and all that we have in HPC, and really help try to really help give our users a new platform, a new method in order to achieve some new scientific results. That some of it's going to be completely new, and some of it's going to be things that they've already tried and haven't been able to get far enough. And maybe, just maybe, this is going to be a way for them to do that. So it's a great initiative, high energy. Again, if you come to this area, we can kind of introduce you to this ecosystem and tell you more about it. Okay, but the first big question is, if you're coming from a pure physics space or a pure HPC space, kind of these two worlds that have a rich history on their own, the question is naturally, why are we integrating quantum computing with HPC? Why are we doing that? The too long didn't read answer is that it's good for quantum computers and it's good for supercomputers. So on the HPC side, and you probably have heard about this if you are in the HPC space, we have a post-Moore's law problem, and we need a solution for that. So we can only put so many transistors on a chip. We can only do so much. We are literally, the level of computing that we're hitting, we're physically and physicsly hitting a wall that we're not going to be able to do a whole lot more with what we have. So one way to do this is, because we're hitting these laws of physics with building these processors, is in one way is to introduce new physics, right? Through the quantum processors. So the one thing is that we've got we're still dealing with transistor and CMOS technology. So maybe the QPUs offer us a new way to do this, a new way to think. Like GPUs before that, we had these big long codes, these massive codes, millions of lines in parallel compute codes. We offloaded those as kernels from GPU. We offloaded them onto the GPUs, and that helped us accelerate our compute to achieve new dimension that we hadn't had before. We're kind of wondering if we're going to be able to do that with quantum as well. So have particular kernels of code that we would be able to offload. So when we have problems, and again, these big legacy problems, things that we've been working on forever, like CO2 situation, when we've been dealing with fusion, when we've been dealing with fertilizers, right? There's all these big problems that we have been attacking for a long time, trying to figure out how to accomplish this. And when we have a new tool in our toolbox, we apply it, like we've done with machine learning, like we've done with other sorts of mathematics and computation. And so now, kind of wondering, could we apply quantum to this to parts of these problems to help us get a little bit further, to help us do it faster, to help us do it more energy efficiently. These are some of the spaces that from the HPC side, we're looking to quantum as to be an interesting solution. And if we can do that, then gosh, maybe we're going to have a radically new computational paradigm to deal with. Now, on the other side, these quantum systems, they, as you well know, they are themselves these physics experiments, right? As you're studying quantum mechanics effects, you have a quantum mechanics system that is helping you study that. I mean, it's just so elegant what's been happening in the physics space over decades. But as we're learning to harness this in this way, in this computational manner, and bringing this into kind of a mainstream space, we are going to need the backing of the massive compute that we have in order to help it. So we have growing computational need, controlling the systems as we get growing number of qubits. We've got the data handling, the staging, the pre and post processing. That's very commonplace for HPC. We've got error correction assistance, noise reduction assistance in order to help us with enhanced performance. We've got different sort of algorithms that we want to look at. These variational algorithms are a particular class that are interesting for us to target and to look at how we might accelerate development and optimization of those algorithms with the testing and the benchmarking. And then you have very complex compilation and runtime environments that are unique to the quantum space. And so with that, we're going to need high computational demand or high computational assets in order to be able to process that. So there's a lot of win-win here if we can sort all of this out. So the takeaway message that I've been using almost since day one is that HPC practitioners, as they're looking at the horizon and seeing these big refrigerators and all that, are looking at this and seeing all the hype that unfortunately, but also part of the domain that we're having with quantum computers right now. The question is, are quantum computers going to replace HPC? And absolutely not. I think that they're going to be incredibly strong in areas that HPC is not, but HPC is going to be offering it a foundation, a legacy. It's going to be offering its own advanced capabilities and complementary together. Hopefully we're going to be able to achieve really big things. So for me, quantum accelerators are HPC. This is high performance computing. This is like a new level, a new definition of supercomputing. So I'm really hoping that we can all get around this concept of supercomputing and what it means in this next phase of our technology evolution. So what do we need to integrate quantum into HPC? Well, again, too long didn't read. There's a lot on many levels. When we first started really thinking about quantum systems coming into our center and how we were going to deal with them and what we were going to do, we broke it up kind of in this very simplistic chart. I like very simple, clean charts. And really simplistically, we had to look at how we bring them in to an HPC system, how they reside in a center like ours, how the hardware interacts with the HPC, the networking, all those pieces. And then, of course, the big chunk is as great as the hardware is, and these systems are, the software is going to be doing the mother's load here of work. And so we have to look at how we're going to bring these two together at that software layer, at that system software layer. And then, of course, all of this is great, but if we don't have good applications, if we don't have a reason to use it, and what good is it going to be for? So we have to really look closely at not just quantum applications that we can kind of contort and squeeze into HPC, but we also want to look at hybrid quantum and HPC application, really that leverages the power of both of those sides. And then the other thing is, and this definitely cannot be understated, is the culture, right? The quantum The quantum community is very much used to using the systems as they're using them more, and they're used to this certain workflows and their vocabulary and their frameworks, their languages that they prefer to code in. And then on the HPC side, we have the same thing. And so as we bring them together, we're going to have to do this in a way that we're not taxing either community too much or as little as possible to get the adoption in order to be able to use this. So this is something that we think a lot about in here. And then those layers kind of on the verticals looks like this. We have to bring in these quantum systems. We have to help harden the technology. A lot of this technology is very nascent and new. And when you come from a perfect, wonderful physics environment where things are controlled, where you have PhD'd quantum physicists taking care of these systems 24/7 and knows every nuance and knows the deep physics of why something isn't working, that's wonderful. But when you bring it into an HPC environment, those people are less common to have, and we have to have more of a production kind of mentality, less hands-on. So we have to harden that technology, and so we want to work with these vendors and work with these spin-ups to be able to help them, give them suggestions for their form factors, for their next generation, for their operational parameters. The other thing, as I've kind of already mentioned, is that we have to enable quantum and HPC working together. We want to be able to have a single source software stack. Right now in the community, we've got quantum software stacks that are developing. We've got the HPC, and that's okay, but then you've got the glue between them, and that works for early stage. But if you really want to optimize this, both as the quantum systems are scaling up and as the HPC systems and environments continue to scale up and diversify, we want to be able to have those tightly integrated and working together more in unison. So that's a big, big thing that we have to work on. And then, as I said before, at the end of the day, all of this, we have to remain user focused and really, really targeted towards the users, because we want to make as familiar as an experience as possible for both sides, and actually not just the HPC users and not just the quantum users, but also the domain users. I tend to forget the third category, but I mean, at the end of the day, there are people that honestly really don't care that their applications are running on a quantum system. They are looking for results, and they're looking for new discovery, new insight that they hadn't had before. And so we need to really be thinking about all of them and making sure that we're attempting to deliver this. The great thing is that we're not starting from scratch, as the saying goes. There's nothing new under the sun. While quantum is definitely a big paradigm shift, we can leverage a lot of the lessons learned from HPC, from the introduction of GPUs. There's a whole lot of lessons that we can learn, but then we can also address the unique newness and specificity of those quantum systems. So just to kind of give you an idea, some of the biggest challenges that we're looking at and that we think about, this is kind of a representation, but if we sat down with a glass of wine, I know that we could come up with a whole lot more. But we have the engineering of the quantum systems and the infrastructure themselves. We have to make these viable and operationally stable. We have to make them, we have to have them follow policies and process. We're starting to talk about service level agreements with quantum systems. We have that hardening of stability and process that we have to think about. In terms of the hybrid software, and I'll talk a little bit more about this in a minute, but we've got resource management, allocation, scheduling across two very different types of systems. And then we also are looking at multiple systems. This is, this exchange for efficiency, dealing with latency. This is something that we really have to think about a lot. We have a very dynamic compilation environment, very dynamic runtime. There's a lot of things in HPC that we sort out kind of pre-compile, where with quantum, there's a lot of dynamic and there's a lot of iterative that has to happen in the compiler space, which makes this really fascinating. And honestly, if you're an HPC person and you think you've got chops in this space and you want to come do something that really tests your mettle and challenges you, I think quantum and what we're doing with a lot of this hybridization is really intriguing space. And then, of course, error correction. So, I mean, that's the big one now, where we are now. We have to think about the redundancy, the resiliency, again, the dynamic resource allocation, a pulse level adjustment, cross validation, continuous monitoring and maintenance. This error correction, because of the stability of the systems currently, not just the inherent nature of the qubits itself, but its reaction to its environment. There are a lot of components that we have to think about to get all of this to work together, to stabilize, and to be able to compute. So we're just getting started. There's a lot of really interesting work to be done, but this kind of gives you a bit of an overview of where our mind is and what we're thinking. So luckily, there's a lot of good funding for quantum computing now. And we're able to also leverage that with programs that we have on the HPC side, because some of the things, some of the issues that we have, like disaggregated compute or disaggregated acceleration, there are these topics that we have also in HPC that we're looking at quantum going, okay, this is a bit different, but in principle, there's some pattern and process recognition here. So what we're looking is to take our funding and kind of put it all together to look at some of the common issues and where we can really leverage the duality of the systems that we're dealing with. So this, and again, I know this is a physics crowd, and so I know this looks probably familiar to you. I have to say, the first time that I saw this, I kind of stood there in disbelief at an optical table when they said, here's a quantum system. I'm like, oh my goodness. But this is from our Max Planck partners, and they're literally just right across the street from us. And this is one of the research systems, obviously, that we work with. So this is the very beginnings of a lot of this, right? Now, I kind of kid, but when I saw that, I first said, oh my goodness, I'm used to clean 19-inch racks. I'm used to, exceptional cable management. And I said, do you have these in like racks? And they said, oh, sure. And then they pointed me to this rack. And obviously this is an exaggeration, but, but as we're moving things from the technical or the physics and the engineering advances and trying to bring it into a production space, there's quite a journey of learning that goes on here. So some of the other pictures, you'll recognize obviously a Dill fridge with the electronic racks next to it. That's fairly common. It looks fairly normal in a setting like this, but in an HPC space, which we have now sitting right next to our compute racks, this is a little bit of an alien beast with different needs and different things that we have to think about. As these companies are advancing, they're thinking about commercial viable designs, and some of them are, very, very aesthetically pleasing, but maybe not as much functional in an HPC center. When you've got very dense, compact spaces, you've got 19-inch rows, and especially if you're thinking later on about hyperscale centers, it's about repetition and repetitive and pipes being in certain places and floor weights being a certain thing. So as we're trying to think about these systems eventually getting to the point that they could be in cloud centers or hyperscalers or HPC centers like ours, we have to start to get a little bit more familiar. And that's an example of two that I have here. So the bottom right is an ion trap system from AQT. What I liked about them is that very much from the beginning they thought about their design fitting in an HPC center, and so they got pretty close to that. But there's still issues, things like dust or like other components that as they continue to develop, you've got lasers there. The sensitivity of the lasers in the environment, as how is their technology going to harden as time goes on that it can be a little bit more robust and viable? And then a company like Quantum Brilliance, they literally just did a blade style that you can shove it straight into a normal 19-inch blade. Still evolutionary improvements to be had as it moves on, but they're thinking in that space a lot more. Okay, which kind of brings us to the Quantum Integration Center that we have at LRZ. So at LRZ, we've got our big compute cube, and when I just realized I didn't provide a picture of that, I'm sorry, but we have this very large 5-story compute cube that houses our HPC systems, our clusters, visualization systems, AI systems, email servers, all of those components. That's our production environment, right? That's the space where we have systems that are under SLAs. That's where we have systems that we don't access that often, that there are no offices in that space. That's really where they're meant to be mature and stand on their own. Then we've got this quantum integration center in another building right next to it, and this is more of our lab space, but our center lab space. So it's it's not the same foundational physics feel, obviously, as like Max Planck and all, but this is where we put systems that we want to work more on high touch with. And you can see kind of in the back there, we've got a cryostat. We have an IQM system that was funded from the German government. This is called our DAC system, and we have a 5-qubit QPU, and now a 20-qubit QPU in there that we use as target for our development and for some of our application work, automatic calibration work, those sort of things. In the middle there, we have this very, very nice AQT ion trap system that came to us late last year, and that is starting to work. We're starting to work with it and really quite enjoying that. And then on the right side, what you kind of see is a bit empty right now, but you'll see 3 blades, 3 nodes in there. This is our HPC test bed. Unfortunately, it's empty because the compute nodes are over in the compute cube right now. They're coming down. We had to upgrade the power, but we've got 3 full racks of this test bed, this HPC test bed, filled with a whole bunch of goodness in there, like CPUs, different GPUs, different FPGAs, smart NIC cards. And basically, that's going to be our HPC test bed for tightly integrating these systems together and developing our software. So the 3 nodes that you do see in the bottom there, those are our quantum access nodes. So one node goes to the cryostat, to the 5-qubit chip. The second one goes to the 20-qubit chip. The third one will go to the AQT. And this is kind of, and I'll talk about this in a moment, but this is part of our build for the matching up the HPC and the QC. Okay, so I talked about this a little bit. This was a system that came to us again last year. It was part of a purchase with for the Munich Quantum Valley, and this was really meant to help us be a target for our quantum software development efforts. And really, really happy to have this. AQT is down in Innsbruck in Austria, and they have a very rich history of very quality physicists and the work that they do. The other thing that we have coming in, this is a BMBF, again, a German federal funded project for neutral atom. And so we're working with a spinoff of Max Planck called Planck. And they are going to be bringing in a neutral atom system into our center in the next few years, and we're very excited about that as well. Again, we just have the pick of the litter of really brilliant minds in our ecosystem, so we're very happy to have them. Now, why are we having all of these different technologies? We're going with the strategy that we would like to have a quantum zoo of resources, and so we've got 3 coming in. I'm looking to add more in. But the idea is that each of these have their own unique characteristics, right? We're very early in this phase. As you know very well, you can build qubits several different ways. There's the physics, there's the different engineering. All of this creates its own unique behavior of compute. And what we're trying to understand is where particular applications or particular algorithms, where the characteristic of the compute fits better for one versus the other. And we want to be able to try, like we've done with different types of GPUs, or actually a better example is different types of like next-gen AI processors and compute behaviors. we want to try to figure out as we're moving forward here what works best with what. And so having a nice zoo of options is really something that we want to bring in-house. We want to be able to turn the dials ourselves to figure things out and to have that freedom as we're trying to develop a unified software stack that still accounts for the specificity of the systems. Okay, so I talked to you about the production environment. So this is an example of that. And as proof, you can see the quantum system, but in the back, you can see that it is in our compute cube. This is the QExa project system. This one is, we're looking, this is going to go live for the users in early summer. So we're very close and very excited about that. This is an IQM system. It's a 20 qubit. And this one is going to be our first production demo. It's a German demonstrator, but a first production system that we're going to make available, again, with the proper user allocation and access models for the Bavarian, the German, the European levels. This is going to be kind of our first run into getting this all set up for our users. On top of that, and I think, let me go here real quick. On top of that, we are one of the 6 centers for the Euro HPC joint undertaking, and we are going to be housing let me go back here, at least a 50 qubit superconducting, and then an upgrade to at least 100 qubit superconducting system. And so, I very optimistically, but incorrectly labeled the 100. That would be very nice, but the 100 qubit system is actually going to be in 26, not 25. That would be fantastic, but yeah, that's a mistake. In any case, what we're doing is we really like superconducting for some of the scalability factor from some of the work that we're doing. And so this line, we're trying to scale up as we go and as we continue to more tightly integrate into our systems. But of course, I've been talking about the quantum systems, but everything is about HPC-QC, how we bring these together. So this kind of also gives you an idea about how we're pairing the different systems with our HPC resources, from our testbed environments to our current SuperMOOC-NG Phase 2 system that's coming in, to our next procurement that's coming in. This is going to continue to be an iterative process as we move on. Okay, so. And then I guess just for funsies, then the purple dot is where the Euro QExa is going to sit in our compute cube. The rendering right now is our QExa system that you saw in the picture, and then right behind it is going to be the Euro QExa system. Okay, so the hardware is definitely what we're investing in and where we're going. However, obviously the simulators play an important role in validating and testing and optimizing and just proving whether a circuit should be on a hardware system or not and what can be done. So we have a couple of resources. We have a couple of Eviden Captiva, as is now called, systems in, and then we also have a scalable quantum software suite on our HPC systems, where we've brought in several different simulators. We've done a big benchmark study that's going to be published here soon, looking at different algorithms, kind of selecting the algorithms as we go and mapping them to these different simulators to get ourselves knowledgeable on this, and then building our benchmark suite that then we're going to start using more for the hardware when those are all up and running and moving forward, etc. Okay, now back to the infrastructure part. As I mentioned before, I mean, we all know error correction is an issue. Decoherence, just the overall sensitivity of the systems is something that we have to deal with. There's inherent sensitivity from the overall qubits themselves, right? Manufacturing imperfections, the physics of it themselves, but then also we all know that the environment plays a big role in this. What we've done is, because we're bringing this stuff into an HPC center, and there's a lot of stuff going on, there's not as much, we can't control things as well. What we wanted to do kind of early on is do a big setup for a big telemetry study for the monitoring. So what we've done is that we've taken many, many different IoT sensors on the outside, from the system itself, from the environmental sensors that we put around it, the cryostat. I mean, we monitor everything from the elevator, weather, you name it. We're trying to pull in as much data as possible. And what we're doing is, and here's a diagram just kind of give you a rough concept. We have, here's a couple of the sensors that we've added on to this. But what we're trying to do is pull all of this sensor data into our data center database, which is something, again, that we're leveraging from our HPC experience. We have thousands upon thousands of sensors on the HPC systems, and all of that pools into this construct that we've built, this data center database. We're doing the same thing with the quantum data, putting all of that in, and what we want to be able to do is apply analysis for it. We're looking at machine learning models, again, that we've done from the HPC space, and what we're looking for are patterns. Our patterns here are triggers. We want to be able to do some predictive operational, I think I have that here, some operational data analytics. We want to have prediction. Again, as we start to see that the system is deteriorating, or that there's an issue, we want to be able to, with the scheduler in our integrated solution, we want to be able to move users easily over to other systems. We want to be able to give them a proper heads up or notification. We want to go ahead and start scheduling calibration events. We want to be able to get to a production state where it's not like, oh my goodness, we need to shut this down, or we need to recalibrate, or we need to do something. We want to be more smarter and more production oriented. And so that's one of the projects that we're working on. We had a paper at IEEE Quantum Week last year, and we've got some other submissions that are going in, and I'm sure several of you are probably also getting ready for that April 22nd deadline on those papers, but we'll have several papers coming out this time as well. Yeah, so this is just kind of some of the pathways that we're looking at. But again, you know, this is meant for some calibration prediction. This is meant for notification system. We also use it for a very, very operational purpose. Just recently, we had a shift in our energy sources. We had to turn on the air conditioning because it was an extra hot day. We're a very passive heat institution. We had to turn on air conditioner because of the temperature spike. That caused a very brief delay on our compressors. Compressors went down for a moment. We had to respond, but you know, with the censoring and all of that, we knew what was happening, or we just get hot on a particular day in a room, and that causes a certain event, or even something as utilitarian as we can tell when the liquid nitrogen has gotten too low. So that's kind of all of what this telemetry study is doing and what we're bringing into this. Okay, so now for kind of the meat of what I wanted to get to, and that is the software part. And so this is really our bread and butter, I would say, of what we're looking to do. So we have the Munich Quantum Software Stack that we've been banging on here for a while. And this is a very simplistic representation, just to kind of give you an idea and to walk you through some of the premise here. But on the left side, you know, we've got these wide user communities. We've got the hardcore physicists that program to the quantum metal, right? We've got the HPC bare metal programmers. We've got in the middle space, we've got the folks that will use directives. We've got the few folks that will use libraries. We've got the folks that really don't even want to touch code or command line, right? So we have this mixture of communities, mixture of domain spaces that are used to particular frameworks, all of this mixture, and now we want to use quantum as another method for compute. So what we're trying to do is have them on one side, and we've got the quantum systems and the diversity of systems on the other side. What we're trying to do is to figure out the best way to have these work together and to get this harmony. So on the left side, you know, we've got the programming languages, we've got the toolkits, the libraries specific to particular domains. Up at the top, we have this web portal. So a lot of times people are still going to want and may want to for a while access the quantum systems directly. So we're providing them a portal access. I'll talk about that in a moment. But then kind of going into that HPC, going deeper in, we've got the HPC route with quantum acceleration. For both of those, we've got, scheduling, resource management, hybrid scheduling of those two working together. When we get to the whole compiler environment, we have to deal with some very unique specificity of quantum systems and dynamic compilation. Comprehensive toolkits, we have to optimize, verify, we have all of those components. And then when we get to the back end, we have to hook in to those various systems, and we need a framework for that. So we call this the Quantum Device Manager Interface, or QDMI, and this is the back-end interface that hooks into the various systems. So what this looks like, so this is kind of the dark blue is the foundation, right? This is where we're trying to establish continuity, commonality, some sort of unison. But then we cannot pay, and that's the commonality of all of it. But we would be remiss to think that we could build one unifying software stack for all systems and be system agnostic. We understand now that's not going to be the case. And so what we need to do is build that foundation, but then account and honor the specificity of the different systems and those compute parameters that I talked about before. So what we've done is that we've looked at this closely and we figured out a couple of spaces, and that's what these custom plugins, this color is. We figured out kind of where there has to be this uniqueness. And what we want to do is to have those in kind of this suite of plugins or APIs, so that basically, and that's kind of the generic picture, the reality is more like this. So we've got the superconducting plugins, we've got the ion trap plugins, we've got the neutral atoms, we've got the superconducting topology X, and we've got, we're moving towards photonics now. We've got photonics this type of way, or neutral atoms this sort of way. So we're looking at the different systems, and we're trying to understand where it's unique, and within the context of these plugins, to allow the specificity of the system. The other thing that we have, and I kind of covered it up, is this figure of merits and constraints. So this is, what are the unique parameters of the system? It's not just T1 and T2 times. It's not just the qubit count or other components. We're going through right now a very careful study of what's common among them and what's specific. And then basically you have a FOMAC library for the system that it then couples with a unique set of compiler passes for that system that then links to the particular backend configuration. You have all that together. You have the programming abstraction on the user-facing more side, and then ideally all of that comes together and functions. So what we've done is we have set this up. We've already been sending shots to our superconducting system. We're getting ready for the ion trap. We've done this also to our simulators, our QLM, as our first targets. So we're making some good progress here. And then also now we're working on them coming back, and we have some early results in the superconducting as well. So this is all starting to form a level of maturity that we can see as we move forward where we need to build. Okay, so I'm going to talk very briefly about the quantum portal, because this is not incredibly new, but this is a real necessity that we need to have. Again, for those quantum direct access points, we make this Bavarian quantum portal. This allows us, for the different user classes that we have, either our local university users, the federal level, the European level, the different policies related to their use, they can log in, they can generate their own token with partial allocation, system assignment, a couple of other parameters, and then they can use that in their codes. Like they can go to Qiskit and the frameworks, they can put a plugin in their code, a very simple code. And then they would be able to send from the Qiskit direct on their laptop, send a shot to the quantum system. So that's kind of on the user side. And then on the administrator side, we're working on token management, security, being able to expire tokens, quickly if need be, account for allocations, projects, all of those sort of things together. And this is fairly standard, I think, across the ecosystem, what we tend to do for HPC, but we're looking at how we can do that with quantum. But then the cool thing is how you do the direct quantum shots coupled with the HPC, because it's still going to have to go that route, and then how you do things like the common scheduling. And again, we're going to have some papers, and I think there's at least one paper and a poster, I believe, for IEEE where we are now. So this is kind of a more detailed picture, and it even goes deeper than that. But kind of the components that we've been building as we go, things that we're thinking about, the different circuit cutting, the different optimizers, the selectors, which I didn't actually talk about in the other picture, but the idea that again, sometimes you're not going to care about what quantum system you're on as time goes on. So we want to be able to analyze your circuits, figure out, which native gates go with which systems, where it's more optimized, and then send it to the right system, or potentially as we go on as to break that up and then to send it to different systems. Now that we've got multiple systems in-house, that's one of the things that we want to start cracking on. Okay. Oh, and you know what? Okay, I think I'm just going to go through this for fun because I seem to have repeated my components here. Sorry about that. Okay. Oh, for some reason, apology, seems to have duplicated. Not really sure how that happened. Okay, well, we'll just take a review journey here. Okay, right. So then just some of the highlights of the Munich Quantum Software Stack. So I said those figures of merits and constraints, that's really important. We've been working very closely, again, with those physics builders, the users of this space, the experimentalists from the actual domain users within our Munich Quantum Valley, and then within our other federal projects, and now into the European space. We've been really looking at what the useful metrics are across the different quantum modalities. We've have initial prototypes for the superconducting and the neutral already established, and then we're working on actually this is a bit old, on the compiler plugins. For optimization and compilation, again, we're working on various things like virtual circuit abstractions, looking to apply AI or machine learning to apply better selection criteria, optimizability, and to advance gate simulation to support these optimization passes. And then for the HPC-QC, the integration, we have the quantum portal. We have a definition of a runtime tool chain that we've been working on for this HPC-QC. And then the one thing I didn't really mention, we're looking at HPC-ready quantum programming models. So we're looking at OpenMP. We've been doing some work on that. We had a paper, a poster, I think, at the last IEEE, if I remember correctly. We're working on a QPI, kind of a offloading passing interface for the quantum offloading from the HPC-based code. So several of these, again, we're trying to repeat history where we can, best practices for that familiarity, but then also accounting for correctly the specificity of the systems that we need to work with. So, I mean, we're one center, and there's many centers, including Barcelona and in Italy, and the rest in Europe, and then worldwide. I mean, we're all realizing that there is a lot of work that we need to do. So there's always strength in numbers. So one thing that we did last year is that the Technical University of Munich, LRZ, iCheck in Ireland, the Supercomputing Center, the national labs of Los Alamos and Oak Ridge. We got together and we went to IEEE and we asked the Quantum Initiative if we could please form a quantum HPC working group. And they said, absolutely. You'll see in this diagram in the upper right, kind of parts of these components that it'll be very familiar to that stack that I was showing you before. We launched at IEEE last summer. We had a BOF at SC. We have an event being planned at ISC. And so if you're interested in this, and you think this is intriguing and you would like to be part of this, please do join us. Again, there's mental strength in numbers. So we would most love to have your intellect to all of this. I didn't have time because I typically always run a little bit late. Of course, I didn't really get into a lot of the applications that we're working with. We have, I call them the hybrid hunters. We've got a couple of folks working on their PhDs that are specifically looking for the best fit characterized hybrid applications, looking for those use cases, looking for ideal, I don't even say quantum algorithms or HPC algorithms, just algorithms with the right characteristics, and then also those particular offload kernels that would be of interest for us to work on. So with that, again, this is my team, and I hope with what I've been able to share with you, you'll also allow me the opportunity that, again, we always are looking for collaborators. We're also looking for people to join our team. So that little "you are here" symbol, maybe that's you. You don't have to be part of our staff. I'm not trying to poach you, although if you want a job, we maybe have some opportunities. But if you want to collaborate with us, again, we're always happy to have conversations and hear some of your clever ideas and approaches, bring them together so that we can all figure out how to do this together. So with that, I know that was a bit of a whirlwind, but thank you so much for your time and for this opportunity to talk to you. And it's been a real pleasure. Thanks.
Sorry, your microphone.
Oh. Oh, can you hear me now?
Sorry. Awesome, Laura. Thank you very much. Thank you. Thanks a lot. And so I think it's time for questions. I see there's a lot of young people in the audience, so maybe they have.
Let me stop sharing, maybe. I've stopped sharing, correct?
Sharing. Please ask questions, anybody.
Maybe can I take an opportunity? I'm just kind of curious for the folks that thought it was interesting enough to come to this. Are you thinking about are you thinking about hybrid and integrating quantum with HPC, or what particular problems do you see, or what are you thinking about? I'm kind of curious.
Mm-hmm. Yeah. Well, certainly. I mean, there are Quantum Spain is inside a much larger initiative in which at the Barcelona Supercomputing Center there'll be emulators, and there'll be other quantum computers than the one that is being built. But certainly, I mean, maybe not at such an impressive scale as you have shown us, but certainly this is in everybody's mind. Me particularly, I'm located in Galicia and the Galician Supercomputing Center, and certainly, I mean, there's a trend towards integrating these two HPC with QPC. I mean, this is certainly I think we are all convinced this is the route. This is the route. I mean, there's no doubt about that. Yeah, maybe I mean, concerning you mentioned the opportunity to collaborate. I think there's a lot of young people that I know from the. Maybe you can comment. Do you have summer boot camps or things like that? The opportunity to.
Mm-hmm. Yes, I mean, I want to say I'm really impressed with Quantum Spain. Like I said, one of my colleagues from my team, Yaknan, he's coming to you next week. In
Benaske.
Yes,
Beneski.
yes, Beneski. So he'll be there next week because Alba had mentioned this was running. So we're super excited about that premise. And frankly, we're coming to learn from you because we want to apply something like that this summer ourselves. We're looking, we're right now, because we've got the systems coming up and all, we want to get folks that we want to move to friendly user phase, right? Because we know that there's some kinks. We know that the software is not going to be perfect. Also from the vendor software, all of that. So we're looking for people who really want to dig in and try things. So we're going to do things like have a hackathon coming up. We're also having what we, it's kind of an odd name. We call it the Q-Beast program. So we have this BEAST program for HPC. So it's Bavarian Energy Architecture and Software Testbed. And what we do, we put all of this cool architecture in a couple of blades, and then we have seminars at the university where the students access it, spend the semester working, benchmarking, doing all that. We're planning a Q-Beast setup for that as well, to really kind of let the students go deep. And to get that sort of experience. Eventually that'll move into the general community. It'll eventually move into industry application, but the students are always so fantastic to work with because they have that energetic spirit and that tolerance as we're figuring things out.
I really encourage everybody. I mean, I did my postdoc in Munich, exactly in the technical university, and it's a lovely place, and the ecosystem is amazing. So I really encourage, if you have stages or things like that people can do. I mean, we would be extremely interested in knowing about that. Yeah. Is there any? I see Guillermo Diaz wants to make a question, so has his hand raised, right?
Yes. Just one thing. Just in case, I think that for the meeting is 1 minute left. I don't know if Teams is gonna close the session. So just in case, if somebody has some question, please, if the session is off, just let us know, and I will forward to you, Laura.
Absolutely. And just before we start, I mean, if any of you are ever in Munich and want to swing by, just email me, connect me with me on LinkedIn. I'm more than happy to share this knowledge. We all have to kind of work together. So please do feel free to reach out. Okay.
Thank you very much. Thank you very much. Guillermo, I think your microphone is on now. You can make
Yeah, I just wanted to ask about something. You have this very impressive flow chart of all of the stack. How would you manage all of these hybrid algorithms and so on? So I'm particularly interested right now in doing circuit cutting, which I believe you mentioned in circuit cutting. So first of all, because you had a large team, are you developing there in the LRC algorithms for circuit cutting themselves, or are you like taking, I don't know, like I know for instance, Qiskit has their own packets and so on, but so that was the first question. If you were already developing stuff which could be more suitable to whatever you are doing, and the second one is, how do you manage the resources requirement for that? Because I mean, circuit cutting, as far as I understand it, like, okay, I have this problem, which is very large, and it's maybe, I don't know, 300 qubits, and I don't have a system of 300 qubits. So I will try to partition it, and then it will require a lot of different resources, more often than not, time. So how would you manage that? Like saying the user, this is completely not possible to be done, even though, I mean, it will take like years and years. What's the process?
So the first question I'll answer is that yes, we are working on some of our own solutions, trying to really understand this. The second one that I'm gonna have to punt a little bit because I'm not the expert in this. I've got to.
Yes, of course.
But I mean, if you ping me, Guillermo, I've got a PhD candidate working on this, and I think there's also a postdoc who's starting to work on this. So I can connect you with them, and they'll be more than happy to go into deep with you. I think they would really be interested, and also to see what you're doing.
Oh, that would be great.
Yeah, sure. Of course.
Yeah. That was a great question. I actually think circuit cutting is kind of the paradigm of integration of HPC with quantum computing. Exactly that is the problem where you want to benchmark this integration. I mean, that's precisely at the core of the. I would say this is. I also had that question. Yeah, that was wonderful. Anybody else? So I think we're not going to risk that the system just shoves us off And I want to thank Laura again for her time and for this wonderful talk. And just as she said, keep in touch, everybody.
And
Yeah.
please, if I can just say one last thing again, it's really exciting to be able to talk to folks like you, because obviously you're interested in this space, and it's such an exciting field right now, and it's like this. I mean, not only is quantum computing incredibly cool and interesting, and so many opportunities, but also connecting with HPC, it's just like this whole other shift forward that we might be able to achieve if we can get all of this to work. So you're in a really exciting space. So all the best to you in your careers, and again. If I can ever be of any help, please do reach out to us. Like I said, we're a good, friendly bunch, and we've got beer gardens. So, come talk to us.
Thank you very much.
So thank you very much, Laura. Yeah. See you again.
Thank you. Bye-bye, everybody.
Goodbye.
Bye-bye.
So thanks, everybody. We meet in